Okay, just to summarize what we did last time, we discussed the birthplace of the stars. We have evidence that they are born in these so-called giant molecular clouds, very large clouds that contain molecular hydrogen, and they are not uniform. There are regions of higher density, so-called clumps, and the denser ones start collapsing under their own gravity, and as they contract, they heat up. So in the process of gravitational contraction, the gravitational energy is transformed into thermal energy, and this star to be, so-called protostar, heats up. And if it's massive enough so that the temperature in the core reaches at least 10 million degrees Kelvin, then it will, the hydrogen in the core will ignite, it will start fusing into helium with the release of energy, and more or less the star has become the main sequence star. The more massive stars clumps take less time to contract than the less massive one, as indicated here. And I pointed out that once their temperature is high enough so that they emit a lot of energy in infrared that can penetrate the clouds, then we can observe them in the infrared once their tracks on HR diagram cross this so-called birth line, which is indicated by the dashed line here. Okay? So once it becomes a main sequence star, its further evolution very much depends on the mass of the star. In fact, if the clump that is contracting is not massive enough so that the temperature in the core never reaches 10 million degrees, it will never become a main sequence star, right? And it turns out the calculations show that if the mass of the contracting clump is less than about 1/12 of the solar mass, which is about 8% of the solar mass, it will never become a main sequence star. These objects become what are known as brown dwarfs. For instance, the planet Jupiter in the solar system, which is the largest planet in the solar system, its radius is about 10 times the radius of the Earth, or 1/10 of the radius of the Sun, could be considered as a brown dwarf. And it turns out that Jupiter emits more energy than it receives from the Sun. And you can ask, well, where does that energy come from that is being produced by Jupiter? It actually comes from its gravitational contraction, right? Just like these contracting clumps, they transform gravitational energy as they contract into thermal energy. The Jupiter is still contracting, right? And that gravitational contraction is responsible for the energy of Jupiter. And in fact, it exceeds the amount of energy that it receives from the Sun. It turns out, as you'll learn closer to the end of the course, that the chemical composition of Jupiter is very similar to the chemical composition of the Sun. About 3/4 it's hydrogen, and 1/4 roughly helium, and small percentage of heavier elements. Okay? So when the solar system, the Sun and planets around them were forming, there was this clump that was bigger than other eventually planets in the solar system, but it wasn't massive enough for its hydrogen to start fusing into helium.